Okay, quick recap on the definition of the matrix of a linear map. So let's say you have a linear map T and you have a basis B of its domain and C of its codomain. Then the matrix of T with respect to the initial basis B and final basis C was the matrix where the jth column told you how to express T of the jth basis element from B as a linear combination of the basis C. So let's suppose we're in a situation where we have two composable linear maps. So the first fact, which we'll actually prove on the next slide, is that when you have two composable linear maps, the result is actually, again, a linear map. So let's suppose we look something like this. So we've got a linear map S from U to V and T from V to W, and we've got some bases for those vector spaces. So B for U, C for V, and D for W. Now, once we've proved that the composition where you do S first and then T is linear, you could ask about what is its matrix with respect to the initial basis B and the final basis D. But of course the matrix of S with respect to initial basis B and final basis C would tell you how to express S of something in B in terms of the elements in C, and the matrix of T with respect to initial basis C and final basis D would tell you how to express T of something in V as a linear combination of basis elements from D. So there ought to be a relationship between this and the matrix of T with respect to the initial basis C and the final basis D, and the matrix of S with respect to the initial basis B and the final basis C. And of course that relationship is that the matrix of T composed with S is the matrix of T times the matrix of S, as we're going to prove once we've checked this important fact that actually when you compose two linear maps the result is a linear map. So let's just prove this. That's really easy. So we have to check two things. If you want a map to be linear, it must respect addition and scalar multiplication. So let's do addition first. So we have S from U to V and T from V to W. There's the picture of what's going on here. So we have to take two things in U and look at their sum. So let's say X and Y be elements of U. Then I have to show that T composed with S of X plus Y is equal to T composed with S of X plus T composed with S of Y. That's the first part of the definition of linearity. So what can we say about this? Well, T composed with S means do S, then do T. So we've got T of S of X plus Y. All right, now S is a linear map. So this is T of S of X plus S of Y. So this is true because S is linear, so it respects addition. Now T is linear, so we have T of something plus something, so that's equal to T of the first something plus T of the second something. Okay, so this time this is true because T is linear. Well, what we have there is T composed with S at X plus T composed with S at Y, and so we've shown that T composed with S respects addition. So similarly, and by similarly I mean using the linearity of S and then using the linearity of T, if you have a scalar lambda and if you've got some element X in U, then T composed with S of lambda X is equal to lambda times T composed with S of X. So that's the second linearity property. You can check that yourself using the same kind of argument that we did there, just using the linearity of S and then using the linearity of T. Alright, so it's actually true that the composition of two linear maps is linear, so it actually makes sense for us to ask about the matrix of a composition. Since we only talk about the matrix of a linear map, we have to know that those compositions are linear before we can even get started. So here is our theorem, which I announced on that slide number 0 there, about the matrix of a composition. So we take a linear map S from a vector space U to a vector space V, and we take a linear map T from V to W. So let's draw this situation. We've got U here, we've got V here, and we've got W here. And S is going from U to V, and T is going from V to W. And then we're going to take bases for each of those vector spaces. So B will be a basis of U, and its elements will be B1 up to BL. And then C will be a basis of V, and its elements will be C1 up to Cm. And D will be a basis of W, and its elements will be D1 up to Dn. And then the claim is that if you ask for the matrix of T composed with S with respect to initial basis B and final basis D, then that's equal to the matrix product of the matrix of T with respect to initial basis C and final basis D, and S with respect to initial basis B and final basis C. So you can sort of think about this as the C's cancelling out. If you want to remember like the form of this result, you can sort of imagine the C's cancelling out, like you were multiplying two fractions together. All right, let's do the proof then. So what we have to do is introduce some notation for the matrix of T and the matrix of S that appear in this theorem. So let's let the matrix of T with respect to this initial basis C and final basis D be Tij. So the ij element is Tij, and we also want some notation for the matrix of S with respect to the initial basis B and final basis C, and that will of course be called Sij. So the ij element of that matrix is Sij. So we're just going to work out what is the ij element of T composed with S, and we're going to see that it is actually equal to the ij element of the matrix product, a matrix of T times matrix of S. So to work out what the elements of the matrix of T composed with S are, well, we have to just evaluate T composed with S at one of the basis elements in B. So we'll look at T composed with S of one of the basis elements from B. So let's say Bj. So that by definition is T of S of Bj. And since we have some notation for the elements of the matrix of S with respect to initial basis B and final basis C, I can rewrite S of Bj in terms of the S's. So this will be the sum from, let's say, k equals 1 up to m of Skj times Ck. So that's just an instance of the definition of a matrix of a linear map. So if you're not quite sure where that came from, go and look up the definition of the matrix of a linear map. Okay, so this is by definition of the matrix of S with respect to initial basis B and final basis C. Okay, now T is a linear map, so T of a linear combination is a linear combination of T of the vectors in that linear combination. So what I mean by that is you can move T through the sum and the scalar multiples. This is the same as a sum from k equals 1 up to m of Skj times T of Ck. Right, now we can use the fact that we have some notation for the matrix of T with respect to the initial basis C and final basis D. That matrix tells you how to express T of one of the basis elements from C as a linear combination of the D's. So what we would have here is, let's keep the sum, k equals 1 up to m of Skj times the sum, this time let's say the sum over I of Tik di, like this. So what should I do? I should go from 1 up to n. Let's tidy that up a bit. I equals 1 up to n. Okay, we're going to collect the terms in di, because let's think what we're doing here. We're looking for the matrix of T composed with S. So the jth column of that matrix will come from asking the question, what scalars do I need to express T composed with S of Bj in terms of the D's? So I should gather together the coefficients of di here. So in order to do that, So we can write the sum in the opposite order, do the sums the other way round. So we'd have the sum from I equals 1 to n of, well, then we would have, moving the other sum through, the sum from k equals 1 to m of, I've got tik times skj, and that is the gathered together coefficient of the d's. Okay, now this formula here is familiar. Right, this is the ij element of the matrix of T times the matrix of S. Okay, but it's also the ij element of T, the matrix of T composed with S. Okay, and we're done.